What are combinations? How is a combination different from a permutation? And how are combinations and permutations related? Well, a combination is related to a permutation from the perspective of, for both combinations and permutations, you've got these different events that you're going to be multiplying the number of outcomes in those events via the product rule. But for all of these events, you're picking from the same group of objects or people or elements. So everything I just stated is exactly what was described for permutations, right? You have this group of 50 basketball players, and from this group of 50, we're going to pick 5 for our basketball team. And because for each of these slots that correspond to one of the positions on the basketball team, we're picking from the same group of 50 players. So here there's 50 possibilities. Then there's 49 possibilities, 48. And we multiply all of these. What we're doing is we're counting the number of different basketball teams of 5 we can make from these 50 players, but including any reorderings. We're saying, like, this is the point guard position. This is the power forward position. So if you put Tim here and Philip here, but then you switch these positions, we look at that as 2 different teams, because now you have Philip at the point guard and Tim at the power forward. Okay, and so a combination is just like a permutation, in that we've got these different events here that we're going to multiply, and for all the events, we're picking from the same group. Whereas, again, as I mentioned, for just a pure product rule problem, that's not the case. We're picking from different groups. We pick a bread, white wheat or honey oat. We pick a meat. We pick a cheese. We pick a condiment. Those are distinct groups. So that's not a permutation or combination problem. But with a permutation or combination problem, for all of your different events, your different slots, you're picking from the same group. This group is like dynamically updating as you go through each slot, right? You have 50 options here. Well, now the group has 49 different options. Okay, but so what's the difference then between a combination and permutation problem? Well, the only difference is that with a combination problem, we don't want to consider reorderings. So for a combination problem, when it comes to the picking of a 5-person basketball team, we don't care if Tim is picked first, Philip second, or Philip's picked first and Tim second. We just want to know the number of different 5-person teams we can pick, regardless of what the order is. That's the difference between a combination and permutation problem. With a combination problem, you don't care about the order. Now, it's extremely important to note that if we're doing the sandwich problem, so we can pick a bread first, a meat second, a cheese third, a condiment fourth. Okay, so we could have white bread here, then turkey, then Swiss cheese, then mustard. Well, we're not counting any reorderings, right? Because you can't pick a turkey first. That's the bread group. This doesn't make sense. You can't do turkey here and then a cheese here, so we're not counting the reorderings. So is this a combinations problem? Absolutely not. Because we're not picking for these different events, we're not picking from the same group. With a problem like this, you're not even thinking about the potential of, in any circumstance, a meat being in the first slot. Here, we are picking from the same group, and you can kind of entertain the possibility of switching the spots, but we're gonna factor that out. Okay, so now, then how do we do this, though? How are we going to count the number of different 5-person teams we can pick from a group of 50 basketball players where we don't care about the order of the players on the team? Well, all we need to do is, so we're going to start by counting the number of permutations. So we know how to do this. That's going to be okay. So if we multiply these out, that gives the total number of teams we can make from this group of 5-person teams from this group of 50 basketball players, but it's including if you've got the same group of 5 players. So let's say we've got Tim, Philip, Marie, Stacy, Logan. Okay, but included in the count, in this count, when you multiply these out, is all of the different reorderings of these 5 players or any 5 players, right? You're counting this as well. So now what we need to do is, to fix this problem, we need to divide out all of the different ways you can reorder a group of 5 people. So we need to take this number and divide it by, so how many different ways can we order any group of 5 people? Well, that's a permutations problem, right? Where we're picking from a group of 5 people for 5 different events, 5 different slots. That's just 5 factorial. 5 times 4 times 3 times 2 times 1. You have 5 options for the first slot, 4 for the second. Okay, so if we take this number here and divide it by 5 factorial, then that's the answer we're looking for. Now, but you still might be wondering, well, why does this work? Well, okay, let's think about this. We can take this number here, which is all of the ways you can arrange 50 basketball players in a group of 5, where you're counting the reorderings. This is 50p5. Okay, but now let's think about this from the perspective of, let me bring this here, from the perspective of, so okay, let me draw a Venn diagram here. So you've got this event, you got 2 events. There's M outcomes here and there's N outcomes here. Let's say event 1 is exactly what we're looking for. The total number of ways you can pick a 5-person basketball team from a group of 50 basketball players, but you don't care about order. Okay, we don't know what this is, but let's just say that's exactly what this is. We don't know how to calculate it yet, but let's just say that's exactly what this is. Now, let's say event 2 is the number of different ways you can arrange 5 people into 5 slots. So 5 factorial. Well, then what does the total count of event 1 and event 2, if they're connected, represent? The total count in this system. The total number of ways that event 1 and event 2 can occur together, which is M times N. Well, okay, we know that one of the ways you can interpret the product rule is that you're taking like an outcome from event 1, one of these outcomes. So one of these groups of 5 people where order doesn't matter. Let's say this group of 5, right? This is, again, M is what we're looking for. So we've got this group of 5 people. If we took a picture of this, we would see this group of 5 people. But then if we looked at another outcome, so another picture, we would never see that same group of exactly 5 people again. We would see Tim more than once. We would see Philip more than once. But we would always see Tim with a different group of people. Okay, so, but the product rule, the way we can interpret it is, we've got this group of 5 people. Okay, but what we're doing is, when we multiply these, we're holding this group of 5 people and cycling through 5 factorial, which is the number of different ways you can arrange these 5 people in a line of 5. Okay, but then we're going to another outcome, a separate outcome, Tim, Philip, Lauren, Kyle, Stacy, or just changing one of these, Tim, Alex, Marie, Sally, Logan, just changing one of these and then cycling through 5 factorial. Then stopping this one, cycling through 5 factorial. So you see 50p5 is equal to M times N. where n is 5 factorial. And that's why if we want to get the number of combinations, the total number of ways we can pick 5 basketball players from a group of 50, but order doesn't matter, what we need to do is take the 50 P5 and divide by the number of ways we can arrange the 5 slots or 5 factorial. And we get what we're looking for, which is the number of combinations. And so the formula then in this scenario would be you do 50 factorial divided by 45 factorial, which is 50 P5, right? This is the number of permutations, 50 factorial divided by 45 factorial, but then we add in the denominator a 5 factorial. And now we have, that's exactly what we're looking for. The number of ways you can pick a 5-person basketball team from a group of 50 basketball players, but you don't care about the order of the basketball players. And in this case, that's referring to the number of combinations, not permutations. You say combinations, not permutations. And the general formula then, so we had NPR was equal to n factorial over n minus r factorial. Well, for combinations, NCR is going to be, so you've got n factorial over n minus r factorial, and then add in a r factorial in the denominator. Okay, now, but with combinations, there's another way you can indicate the way we say this is n choose r. You don't say this is just like n PR. Maybe you could say n pick r, but when you say n choose r, when you use the word choose, then you're indicating a combination. That's the convention, which is kind of confusing because you tend to always want to just say choose. Sometimes you'll hear people say choose even though you're talking about a permutation, but the convention is when you hear choose, you're typically thinking combination, n choose r. But here you wouldn't say choose, you just say like permutations or something, but maybe n pick r. It's kind of interesting. Okay, but you can also write it this way. This is n choose r, NCR. This is the combinations of, you're picking from a group of n r items. But you don't do that. This does not mean permutation. No. There's nothing, if you're using this parentheses symbol here, that's for combinations. And this comes from the binomial theorem. So the binomial theorem allows you to expand out any binomial, so like a plus b, to any power. It gives you like a shortcut to be able to do this. So a binomial to like the 50th power, you can use the binomial theorem to quickly expand this out, and the coefficients of the terms are based on this here, which is the binomial coefficient, which is just this n choose r. Okay, now, just like we talked about with this NPR formula, we're going to see that you can have combinations problems that are a bit more complicated than just being able to plug straight into this formula. But however, this is still the fundamental combinations formula. Same here for permutations. The fundamental permutations problem is you want to count the total number of ways you can pick r elements from a group of n elements. But this allows for the fact that you could be wanting to count how many ways you can order 5 items, because then in that case you're just saying how many ways can I pick 5 items from a group of 5 items, and this formula just results in 5 factorial. Okay, but here this is the fundamental combinations formula. It's that basic problem where you're asking how many different ways can I choose r items from a group of n items. Now, for the case where you're choosing like 5 items from a group of 5 items, well, what happens there? Well, you're not allowing for reordering, so there's only one way you could do that, When it comes to combinations, the only, if it's 5, choose 5, well, it's just 1 because you don't care about the order, right? So n choose n factorial over, that's 0 factorial times n factorial. 0 factorial is 1, 1.